An agent communication protocol, ACP, is essential for enabling seamless interoperability and collaboration among autonomous software agents. It defines the rules, message structures, and interaction patterns that govern how agents exchange information and coordinate actions within a system. By providing a standardized communication framework, often including message performatives, content languages, and ontologies, ACPs allow agents to understand each other's intentions and respond accordingly, regardless of their internal architectures or implementation details. This shared language is critical in heterogeneous environments, where agents from different sources must work together. ACPs facilitate complex behaviors such as negotiation, delegation, and synchronization, making coordinated multi-agent interactions both possible and efficient. Ultimately, the use of ACPs enhances system performance, scalability, and modularity, supporting the development of robust, distributed AI systems capable of adapting to changing requirements and growing operational demands. Standardization plays a pivotal role in enabling diverse software agents to communicate seamlessly within multi-agent systems. By defining uniform message formats, communication protocols, and interaction patterns, standardization eliminates the need for custom integrations and ad hoc solutions, significantly reducing development complexity and cost. A standardized communication framework enhances interoperability, allowing agents developed on different platforms using various programming languages or architectures to exchange information effectively. This promotes the integration of heterogeneous agents into a cohesive system without requiring major adaptations. Moreover, standardized message structures minimize the risk of misinterpretation. They ensure that all agents understand the meaning, intent, and context of exchanged messages, which is essential for reliable coordination and decision-making. Without shared standards, agents would effectively be speaking incompatible languages, leading to communication breakdowns, poor coordination, and constrained system growth. Standardization is thus foundational for building scalable, modular, and robust multi-agent systems capable of functioning efficiently in complex distributed environments. Messages in agent communication protocols follow a structured format that combines both syntactic clarity and semantic meaning, enabling effective interaction between autonomous agents. Each message typically includes a performative act, such as inform, request, agree, or refuse, which conveys the intent of the sender. Additional fields include the sender and receiver identifiers, ensuring that messages are accurately routed and attributed, and the content, which contains the actual data or proposition being communicated. Some ACPs also specify fields like conversation ID or ontology to maintain context and enhance interpretability. This structure allows agents to not only read the content of a message, but also understand its purpose, enabling them to make context-aware, autonomous decisions. For example, an informed performative tells the receiving agent that a particular fact is now true or relevant, prompting it to update its internal state or initiate a response. By formalizing message construction, ACPs ensure agents can communicate meaningfully and reliably, forming the backbone of intelligent coordination in distributed systems. Agent communication protocols often employ a layered architecture to structure and streamline agent interactions, ensuring both reliable message delivery and meaningful interpretation. At the base is the transport layer, responsible for establishing reliable communication channels between agents. It manages data transmission, packet integrity, and network connectivity, akin to how TCP/IP ensures robust delivery in traditional networks. Above that lies the message layer, which structures the actual content of communication. It defines message formats, performatives such as inform, request, and sender-receiver identifiers, similar to how SMTP structures email messages with headers and delivery rules. At the top is the semantics layer, which enables agents to interpret the meaning and context of messages. This includes understanding the intent behind a performative and processing content using shared ontologies, much like how an email client interprets text, attachments, and formatting. This layered design promotes modularity, flexibility, and clarity, separating concerns across communication functions and supporting scalable, interoperable agent interactions in distributed systems. Consistent message formats and predefined semantics in agent communication protocols are essential for enabling autonomous agents to coordinate complex tasks without human intervention. These structured messages allow agents to exchange information with precision and understand each other's intentions and commitments clearly. In practical applications like supply chain management, agents representing different stakeholders, such as suppliers, manufacturers, and logistics providers, communicate using standardized messages like request, propose, and confirm. This standardized interaction sequence allows agents to negotiate delivery schedules, prices, or inventory terms efficiently. Because each message carries both structured data and semantic meaning, the communication is both machine-readable and context-aware. This minimizes misunderstandings, reduces manual intervention, and accelerates decision-making, ultimately improving workflow efficiency and system responsiveness. By enabling such high-level coordination through shared message protocols, ACPs make it possible for intelligent agents to collaborate across organizational and technical boundaries in dynamic real-time environments. Effective agent communication architectures rely on standardization, message clarity, and protocol layering to ensure seamless, reliable interaction. These principles underpin various system designs, allowing agents to operate across diverse computational environments. In client-server models, standardized message formats support structured request-response cycles, enabling reliable data exchange and centralized coordination. Agents in this model often act as clients requesting services or information from designated servers. In peer-to-peer systems, where agents communicate as equals, shared protocols and consistent semantics are essential for maintaining symmetric, decentralized interactions. This model supports resilience and distributed decision-making. Service-oriented architectures, SOA, introduce a dynamic layer of flexibility by allowing agents to publish and discover services at runtime. Through standardized service descriptions and communication protocols, agents can interact fluidly, forming ad hoc collaborations based on available capabilities. Mastering these communication principles equips system designers to tailor ACP implementations across architectures, promoting scalability, adaptability, and interoperability in multi-agent environments.